Okay, so now what we found was that basically n combination, n permutation R is the same thing as n combination R times R factorial times R factorial, and R factorial is, and what that means is that, well, of course, n combination R is n permutation R divided by R factorial. So now let's try to prove this thing. So as a proof, we said that corresponding to each combination of n combination R, we have R factorial permutations. We said that corresponding to each combination n combination R, we have R permutations. I'm sorry, R factorial permutations. R factorial permutations. Because R objects in every combination can be arranged in R factorial ways. And this is a very logical and absolutely correct statement, because R objects in every combination can be rearranged in R factorial ways. Can be rearranged in R factorial ways. And we saw that this over here in the previous example, that you would get all of these different combinations, and that the number of these combinations is of course going to be R factorial. Is of course going to be R factorial, because you have, for example, over here you have taken 5 combination 3. So 5 combination 3 is basically, at the end of the day, you are always going to have 3 objects here, and these 3 distinct or different objects here, and these 3 different objects are basically changing here. The order of them is changing, meaning that ABC, ACB, BAC, BCA, and so on and so forth. So the only thing that is changing here is the order of those objects. The objects remain the same. And we already know enough and well about permutation. We know that the permutations of basically R different objects would be, of course, R factorial, because, for example, the permutation of R different objects taken R at the time is R factorial, because we know that n permutation R is equal to n factorial divided by n minus R factorial. Of course, I have to write this way, right? Now, if n is equal to R, then we have n permutation n is the same thing as n factorial over n minus n factorial, and we know that n minus n factorial is equal to 0, basically, which is 0 factorial, which is 1. So this is equal to n factorial. Or if n is equal to R, I can write the same thing as R permutation R, which is the same thing as R factorial over, well, R minus R factorial. Again, I will get R factorial. So So then you could say that basically when you have R objects and taking them all at a time, and we are calculating permutation, we are always going to get R factorial. So that means that all the different permutations related to 3 distinct and different objects is always going to be equal to 3 factorial. If the number of objects becomes 4, then it becomes 4 factorial. Then the number of objects becomes 3, becomes, for example, 5, is 5 factorial. If the number of objects is R factorial. So what that means is that then basically then we can say that corresponding to each combination and combination R, we have n R factorial permutations, because R objects in every combination can be arranged in R factorial ways. It's very clear, very simple to understand. And so, hence the total number of permutations, is of n different things taken R at a time, is basically, so this is the total number of permutations, don't forget this, this is the total number of permutations of n different things taken R at a time, is n combination R times R factorial. Which means that, and then of course I can then write this statement as the total number of permutations of n different things taken R at a time is n permutation R is equal to n combination R times R factorial, which means that, and I know that n permutation R is the same thing as n factorial divided by n minus R factorial, is equal to n combination R times R factorial. And so what that means is that then n combination R is the same thing as this divided by this, which means that n factorial divided by n minus R factorial divided by R factorial. So that's the formula that we were looking for. And here basically R, and here basically 0 is less than R, less than or equal to n. Meaning that R cannot be equal to 0, but it can be less than or equal to n, right? Now from this expression that we said that n permutation R is equal to n combination R times R factorial, what we can conclude, so we said that n permutation R is the same thing as n combination R times R factorial, and basically 0 is less than R, less than or equal to n. What we can conclude from here is that basically is basically the same thing that I've written over here. You can conclude this one, of course. And in particular, if n is equal to R, or if R is equal to n, which would be the same thing, you would have n combination n is the same thing as basically n factorial over n minus n factorial divided by times n factorial. This would be 0 factorial, which is equal to 1. And this n factorial and n factorial you can cancel out, you will get 1. That means that n combination n is equal to 1. And what that means is that you have n different objects, and you are taking the combination of those n different objects taken n at a time. For example, you have 4 different, you have 4 people, for example. You have 4 people. And from these 4 people, you want to select a group of 4 people. This 4 refers to this n over here. This 4 refers to this n over here, and you know that 4 is equal to 4, and so n is equal to n, right? So when you want to select a group of 4 people out of 4 people, there is only one way of doing that, and so n combination n is equal to 1, right? And we are going to use all of these things, and these are important. You need to remember them and you need to understand them, because we are going to use all of these things in every part of mathematics, I would say that, and particularly in, for example, in the binomial theorem. And then you're going to use the binomial theorem in series and all of those things, counting all the way up to infinity. And so basically, if you don't pay attention here, you're going to actually understand, well, practically nothing. So you need to be careful about all of these things, because these are absolutely important. Absolutely important. Okay. Okay, so and there is one more thing here that we define. Basically, you can get this based on of course, well, the formula. As far as we know, we said that n permutation r is the same thing as n combination r times r factorial. And we said that basically 0 is less than r, less than or equal to n. That means that basically r cannot be equal to 0 in this formula. So now, in order to sometimes you do things in mathematics because you want to basically connect something to some other place. And if these connections are not there, then you will get into trouble when you are doing other things. So now, for example, this formula, when 0 is not basically, when r is equal to 0 is not defined here, then you would get into trouble when you're doing other things. And so you have to kind of do some sort of definition. And of course, you have to define things in such a way that what you do, of course, is logical, makes sense. Of course, that's a tricky concept. I mean, making sense when it comes to definitions in mathematics. But you have to do it in such a way that you don't get contradiction relative to all other things in mathematics. And which in and of itself is a pretty tricky thing to do, because there is almost no way to know what's going to happen. Maybe you can sometimes figure out things based on algebra and things like that, But then you might get into trouble, so you need to be careful about that, because contradiction is, of course, as you know, is not mathematicians don't like contradiction. So when you define something, you have to be careful not to contradict something that you have that you've said before. Otherwise, you have to kind of change your definition or make some changes to that or something like that. Now, anyway, for this formula, for r to be defined at r is equal to 0, so what we can say that we define n combination 0 is equal to 1, which means that basically the number of combinations of n different things taken nothing at all is considered to be 1. What this means is that the number of combinations of n different things of n different things taken nothing at all is considered to be 1. Meaning that what that means is that you have basically n different things, and well, taking nothing at all means that you leave everything behind. And well, they have found a good reason, and the reason actually happens to be working with, as far as we know so far, it happens to be working with every other part in mathematics. And they have come up with the reasoning that, well, taking nothing at all means leaving everything behind, meaning that you're not selecting anything. And so that can only be done in only one way, that you leave everything behind. And so based on that, the number of combinations of n different things taking nothing at all is equal to 1. That's a definition. That is a definition. And of course, you know that reasoning is a tricky thing, because the kind of reasoning that you use depends on the kind of framework that you are in. Meaning that, for example, some kind of reasoning works in some kind of framework, and something might seem to be completely reasonable in some other framework, but then that, if you bring that sort of reasoning into some other framework, it might actually not work over there. That's a tricky thing. Now, all of what we call reason in mathematics is the kind of reason that works in mathematics. And so basically, based on that, there is no condition on reason that reason has to be something like this, or has to be something like that, or these conditions have to be basically imposed on reasoning, and so on and so forth. Mathematics is just a mysterious thing, and everything that we have basically come up with in mathematics, and every definition that we have in mathematics, is actually the kind of thing that, well, happens to work in mathematics. And so that's basically the story of reason. Now, basically the reasoning that they have used here is that counting combinations is merely counting the number of ways in which some or all objects at a time are selected. That you already understand. Now, selecting nothing at all is the same as leaving behind all the objects, and we know that there is only one way of doing that. And so this way we define n combination 0 as 1. That's basically what they have done. Now, number 3, we have, so we said that basically n combination 0, we said that n combination 0 is equal to 1, which is equal to basically n factorial n minus r n minus, well, of course, you know that n combination r is equal to n factorial n minus r factorial times r factorial, which is the same thing as n factorial over n minus 0 factorial times 0 factorial, which is the same thing as n factorial over n factorial times 0 factorial, which is the same thing as 1 over, well, this is also 1, so 1 over 1 is equal to 1. So that means that basically, what that means is that, of course, it has nothing to do directly with what I did here, but what it means is that we already have defined r is equal to 0 in this formula as well. So that means that I can say that n permutation r is the same thing as n combination r times r factorial, and that means, and that is basically 0 is less than or equal to r. There was no equal here, there was only less than or equal to n, right? And so based on this, I can say that n combination r is the same thing as then n factorial over n minus r factorial times r factorial, as basically 0 is less than or equal to r, less than or equal to n. So that is now the formula for combination, and it contains, and in this formula r can actually be equal to 0 as well, right? And that there is a couple more things here to talk about as well, and after that we have a couple of theorems and things like that. Okay, so the next thing that we have here is basically n combination n minus r is the same thing as n combination r, meaning that if you have n objects and you select basically r of those objects, n objects taken r at a time, calculating combination, that's the same thing as calculating the combination of n objects taken n minus r times at a time. So how you can calculate that, of course, is that n combination n minus r is the same thing as n factorial over n minus r factorial over n times n minus r factorial, and that is equal to, so you know that basically n minus n is, so you know this thing is n minus r factorial is the same thing as n minus n plus r factorial, which is the same thing as, you can cancel these two out, you'll be left with r factorial. So that would be the same thing as n factorial over basically n minus r factorial times r factorial, which is the same thing as n combination r. So that means that n combination n minus r is the same thing as n combination r. That's also something that you will be able to use in different situations, at least in this book. So you need to know that. And what that means is that selecting R objects out of N objects is the same thing as rejecting N minus R objects. It's the same as rejecting N minus R objects. I don't understand the meaning of that statement, but at any rate, N combination N minus R is the same thing as N combination R, right? And one more thing that you can use at least in this book, of course, you can use combination and permutation to come up with any sort of result that you might need or you might like, because it's simple algebra. You can do whatever you want to do with algebra. But if you have N combination A is equal to N combination B, that implies that A is equal to B, or basically A is equal to N minus B, which means that, and this means that basically N is equal to A plus B, right? So if you have N combination A is equal to N combination E, that implies that either A is equal to B or A plus B is equal to N, right? And you need to, most people do not really understand the meaning of this implication. This implication is not as simple as it seems to be. So when you say that, for example, A implies B, okay, so now I had to search a little bit, and basically this kind of material, you can find it in NCERT mathematics, mathematics class 11, chapter 14, which is called, the chapter is called mathematical reasoning. Okay, you can find all such information in here. Now, this kind of thing is not as simple as it seems to be. It's actually a little bit tricky, and there is actually a truth table related to this thing that we call implication. Now, if I have, for example, P implies Q, if I create a truth table for this, and if this is P and this is Q, so of course you're hopefully familiar with basically mathematical, if a statement is true or false and so on and so forth. Now, if Q is true, it doesn't really matter whether P is true or false. It doesn't really matter whether P is true or false. Then P, then Q, or P implies Q is going to be true. That's basically how this implication actually works. And if Q is false, if basically P is true, then this is going to be false. If this is false, and this is also false, then this is going to be false as well, right? So this works this way. Now, this is the truth table related to P then Q, and you read this as P then Q, or P implies Q, right? So what that means is that if you're Q, and you write this as well, P then Q, or P implies Q. So what this means is that if you're Q, and of course it seems to be, at least in my mind, it seems to be it seems to be upside down, meaning that basically the condition is actually over here, and well, I in the beginning I had a hard time accepting the whole thing, but it's been built like that, and there is no way around, and you just have to accept it, and you just have to learn the way that it works. So what that means is that if your Q, which is, well, I would call it your condition, if your condition is true, which is these two cases, it doesn't matter whether this statement P is true or false, P then Q is going to, in both cases, is going to be true. And if your condition is false, then it doesn't really matter whether P is true or false, then P then Q is going to be false. Now let me show you the truth table over here, and hopefully we can I found a good truth table over here on the internet, so you can see that over here, when B is true in this case and in this case, whether A is true or false, you're going to get true over here for A then B, or A implies B. And when B is false in these two cases, in this case and in this case over here, it doesn't really matter. Okay, so there is something that I said here which is not absolutely right. So when B is false, or when Q is false, if A is also false, here you're going to get a true. This statement is going to be true. Otherwise it's going to be false, right? So this is the truth table of P then P implies Q. And if you want to have some sort of other explanation for P implies Q, that's how you can learn it as well. So basically P implies Q, which is basically this conditional over here. What that means is that this says that that the number is multiple of 9 implies that it is a multiple of 3. So let's say that we have two statements over here. So let me go up here and find some space here, and so when we have basically, let's say that I have two statements here. Let's say that the statement P is a number is a multiple of 9. A number is a multiple of 9, and let's say that you have another statement, which is that the number is a multiple of 3. The number is a multiple of 3. Now if I write P implies Q, which would be the same, which I could also write this way, P implies Q, what that means is that what that means is that then P, I can say that a number is a multiple of 9. This statement would be a number is a multiple of 9 implies the number is a multiple of 3. Is a multiple of 3. So this is my P and this is my Q, and this is implies. So that you, instead of this, you also use basically the implication sign, whatever you want to call it, that it works that way. So what that means is that that the number is a multiple of 9 implies that the number that it is a multiple of 3. Now what this means also is that basically P is a sufficient condition for Q. P is a sufficient condition for Q. P is a sufficient condition for Q. That means that if a number is a multiple of 9, this is a sufficient condition for Q, which is the number is a multiple of 3. And what that means is that this says that knowing that a number is a multiple of 9 is sufficient to conclude that it is a multiple of 3. So what this means is that knowing that the number is a multiple of 9 is sufficient to conclude that the number is a multiple of 3. Is a multiple of 3. That is the meaning of this part. So that means that P is a sufficient condition for Q, meaning that knowing that this statement is true is sufficient to conclude that Q is true. Or knowing that basically a number is a multiple of 9 is sufficient to conclude that the number is a multiple of 3, and it is actually so, meaning that there is nothing wrong with this statement really. Okay, so far we have no problem. So we said that P is a sufficient condition for Q. You need to learn this exactly the way that it is. Basically P is a sufficient condition for Q, and well, I think it's helpful to also learn this example as well. This is the kind of example that you might remember basically always, that you might be able to remember all the time. And so then based on this example, then you will be able to understand P implies Q much better, of course, because when I say that, for example, P is a sufficient condition for Q, then I mean it's possible that I might not be able to then even understand what this statement actually means. It's actually in my personal case. I don't know about you. If you can learn this statement without learning any examples, that's fine. But for me, what I found is that I do need basically this example because I have kind of learned these statements, the meaning of these statements based on this particular example. And then when I get to different cases, I try to interpret those cases, basically having the implication connective or the implication conditional based on that example. That's what I do. Now, so P is sufficient condition for Q, meaning that, for example, knowing that P is true is sufficient to conclude that Q is true, meaning that knowing that the number is a multiple of 9 is sufficient to conclude that the number is a multiple of 3. And it's actually true, because if a number is a multiple of 9, it has to be a multiple of 3, and then you need another factor of 3 so that the number can be a multiple of 9. So that makes sense. And there is one more meaning related to this, which is not very straightforward, but basically when you say P implies Q, you can read this as P only if Q, right? You can read this P only if Q, meaning that for example in the context of this example here, you can say that basically a number is a multiple of 9 only if the number is a multiple of 3. So that makes sense, and that's basically no specific kind of meaning or anything like that. It's just another way of understanding the same thing. And also there is one more thing that, and so of course you can simply forget about this, but you need to remember that, for example, when they say P only if Q, that's the same thing as P implies Q. So that's the exact same thing. So then basically I can write this P only if Q, basically. That's basically all mean the same thing. And there is one more important thing here that you need to understand, and that is Q is a necessary condition for P, which is Q is a necessary condition for P. So Q is a necessary condition for P, meaning that when a number is a multiple of 9, it is necessarily a multiple of 3. When a number is a multiple of 9, it is necessarily a multiple of 3. So, and this means that Q is a necessary condition. That means that Q is a necessary condition for P. And of course, what that also means, which is not very relevant or important here, is not Q implies not P. Not Q implies not P. That means that basically this means that if the number is not a multiple of 3, if not Q is true, then if a number is not a multiple of 3, then it's not a multiple of 9. So that is basically basically stated this way, that not Q implies not P. So that means that if you have P implies Q, that automatically means that not Q implies not P. That's the meaning of this thing over here. So now, of course, if you know the truth table related to P and Q and P then Q, that would look like something like this. Meaning that you have over here, you have, for example, P, you have Q, you have P then Q, or P implies Q. And then we said that when Q is true, if Q is true, it doesn't matter whether P is true or false. In both cases, P then Q is going to be true, which is the case here. Now, when Q is false, you're going to get a false here if P is true. Otherwise, if P is false, you're going to get a true here, right? So what this means is that now let's basically consider each of these cases individually, one by one, and understand them in the context of the example that we have. So we said that if Q is true, then if P and Q are both true, then PQ then basically P then Q is true. That means that basically if P is true and if Q is true, then P then Q is true. Or if P is true and Q is true, then P implies Q is true. That means that if both of these statements are true, then P implies Q is true. Which is pretty simple. You don't even need to think about that. And if Q is true and if P is false, even in that case, P implies Q is true, right? So if Q is true, meaning that if the number is a multiple of 3, even if P is false, P implies Q is going to be true, right? Now, if Q is false, even if P is true, P implies Q is going to be false. Meaning that over here, if your Q is false, even if your P is true, P implies Q is going to be false. And if both P and Q are false, meaning that if Q is false and if P is false, then P implies Q is true. Which is a weird thing in my opinion, in my humble opinion, but it works with the other parts of mathematics. And when you basically learn the whole thing together, then it will not basically seem to be very weird. So that's basically that. Now let's now that we have understood basically the P then Q, now let's go over here and basically the last part of those remarks related to combination was basically, we said that if n combination A is equal to n combination B, that implies that A is equal to B, or basically A plus B is equal to N, right? Because N is equal to, or N is equal to because over here A is going to be equal to N minus B, n minus b, and so n is going to be equal to a plus b. Which means that basically what this means is that then again you can consider the truth table. If you can take this, you can take any of these two, basically any of these two conditions for Q, and you can take this statement as P. And so we said that basically if Q is true, then if Q is true and if P is true, then P then Q is going to be true. If Q is false and if P is false, then P then Q is going to be true. And also so the truth table was something like this. So you have basically P then Q, you have P over here, you have Q over here. So we said that if Q is true, it doesn't really matter whether P is true or false. It's going to be P then Q is going to be true. If Q is false, if you have a false over here as well, you will get the true over here. Otherwise, you will get a false over here. So this means that then if Q is true and if P is true, then P then Q is true. If Q is true and this is false, then still the whole P then Q is going to be true. If both of them are false, then P then Q is going to be true. And also if Q is false and P is true, then P then Q is going to be false, which is not really relevant here. What is relevant here is to learn that in terms of those expressions that I just showed you, meaning that the two important statements that you need to learn here in order to understand such basically conditionals is that you need to learn these two statements over here. That I don't know where the whole thing was. So over here what we said was that basically P is a sufficient condition for Q, meaning that knowing that basically P is true is sufficient to conclude that Q is true. And also Q is a necessary condition for P, meaning that when a number is, meaning that when Q is true, it is necessarily, then Q is necessarily true. So now let me write these a little bit more simply so that we can understand them. So this statement over here, which is P is a sufficient condition for Q, P is a sufficient condition for Q. I can write this as knowing that P is true. What this means is that knowing that P is true is sufficient to conclude that that Q is true, right? So this is one thing. So P is a sufficient condition for Q means that knowing that P is true is sufficient to conclude that Q is true. And also over here we said that Q is a necessary condition for P. Q is a necessary condition for P, meaning that when basically when P is true, Q must be necessarily true. When P is true, Q must necessarily be true. Right? That's the meaning of these two things over here. Now let me make a screenshot here if it's possible. And then I'm going to go back down, go back here. Now let's understand this basically this conditional using the two different ways of understanding P implies Q. So if I take this as P and if I take this as Q, we said that P is a sufficient condition for Q, meaning that knowing that basically this statement is true, knowing that P is true, is sufficient to conclude that this statement is true. Meaning that if I know that n combination A is equal to n combination B is true, that's sufficient to conclude that this statement is true, meaning that either A is equal to B or n is equal to A plus B, or both are true, right? Now that's the first part. The second part, I said that Q is a necessary condition for P, meaning that when I say that P is true, meaning that when I say that n combination A is equal to n combination B, then this statement has to be necessarily true. And what that means is that when I say that this statement is true, that means that either A is equal to B or A plus B is equal to n, or both of these statements are true. And of course I'm saying either this or that or both of them because I'm using or here. So that's the right way to understand these conditional statements. Now I'm not going to, I have already once I have basically done this, the algebra here, and if you simplify this thing, you will get to the same thing basically. So you can use it in your, calculation or whatever you might have. So there is no problem there. Now, there is one more thing here that we need to take care of before we can move further, and that is theorem number 6. That is theorem number 6, which is n combination R plus n combination R minus 1 is the same thing as n plus 1 combination R. Okay, that's the theorem that we want to prove here. So we have n combination R plus n combination R minus 1 is equal to n plus 1 combination R, and we want to prove here. And so basically we have as the proof what we have is basically the left hand side of this equation is n combination R plus n combination R minus 1. That is equal to, basically, based on the definition of combination, we said that n combination R is equal to n factorial over n minus R factorial times R factorial. That's the definition or the formula that we use, that we came up with for combination. So I can use it over here. Okay, so now, based on this formula, I can basically rewrite this. I can rewrite this expression as this is n combination R, so n factorial over n minus R factorial times R factorial plus basically n factorial over, this would be n minus r minus 1 factorial, which is the same thing as basically n minus r plus 1 factorial, n minus r plus 1 factorial, and then again you have r minus 1 factorial. You have r minus 1 factorial. So that's basically that. And so you have and now you need to basically find a way to put these two together. So you have n minus r factorial times r factorial. Over here you have r minus 1 factorial times n minus r plus 1 factorial. And so what we need to do is basically r minus so over here I have n minus r factorial, over here I have r factorial, r times r minus 1 factorial. So you can write this as this part over here, you can write as n factorial over n minus r factorial, not changing anything in there. And r factorial, you know that you can write it as r minus 1 factorial times r. So you can write this as r minus 1 factorial times r. And the reason why you can do that, we have already talked about this in the exercises, but you know that basically if you have r factorial as we have over here, when you have r minus r factorial, that's the same thing as 1 times 2 times 3 times all the way up to r. And of course I can write this as times, for example, r minus 1 times, for example, r minus 2 times, for example, r minus 3, and so on and so forth. Now you can see that basically over here, this thing 1 times 2 times 3 all the way up to r minus 1 is the same thing as r minus 1 factorial. And there is an r over here, so that means that r factorial is the same thing as r minus 1 factorial times r. And that's basically what I have done here. So r factorial, I've written it as r minus 1 factorial times r, right? And then the next thing that we have here is, well, n factorial over, we have n factorial over r minus 1 factorial times n minus r plus 1 factorial, which I can write as basically n factorial over r minus 1 factorial. I'm not going to change anything about that. And then n minus r plus 1 factorial, you can write it as r minus 1 factorial, n minus r plus 1 times n minus r factorial. Let me see. So r minus 1 factorial I have over here, n minus r. So over here I have n minus r plus 1 factorial, and that they have written it as n minus r plus 1, n minus r plus 1 times n minus r factorial, times n minus r factorial. So so you can do that. You can do that because so if you, basically n minus r plus 1 factorial is the same thing as 1 times 2 times 3 times all the way up to n minus r plus 1. Now if I want to get the term that comes before this, I would get n minus r factorial. Of course, the term before this would be, if I subtract the 1 from here, I would get n minus r. And so this part over here would be n minus r factorial, right? N minus r factorial. And so n minus r plus 1 factorial is the same thing as n minus r factorial times n minus r plus 1, which is what we have written over here. So that means that basically n minus r plus 1 factorial, you can write it as n minus r factorial times n minus r plus 1. N minus r plus 1. Which means that you can take basically the n factorial you can take out, and r minus 1 factorial you can take out, and n minus r factorial you can take out, and multiply it by n minus r factorial, r minus 1 factorial. So this would be 1 over r. This would be 1 over r, and over here I would have 1 over n minus r plus 1. 1 over n minus r plus 1. And so if I basically take over here, take the LCM as, so I can write this as n factorial over r minus 1 factorial times n minus r factorial, and over here I can write this as r times n minus r plus 1, and then I would get basically n minus r plus 1 plus r, and then r and r you could cancel out. You would get n plus 1 over basically this thing, which you can write as basically, if you multiply these two things, you would get n plus 1 times n factorial divided by r minus 1 factorial times n minus r factorial times n times r times n minus r plus 1. And of course you know that n factorial times n plus 1 is n plus 1 factorial, because n factorial is the same thing as 1 times 2 times 3 times all the way up to n. Now n factorial times n plus 1 would be equal to this whole thing. So if I multiply this by n plus 1, I would get basically this whole thing times n plus 1. So then this basically all of these terms multiplied together, of course, is n plus 1 factorial. So n plus 1 times n factorial, I can write it as n plus 1 factorial. N plus 1 factorial. And the denominator, I can write it as r times r minus 1 factorial. So n minus r plus 1 and minus r plus 1. Okay. So you see over here we have two things that we can basically put together. First of all, we have basically r minus 1 factorial. We have r minus 1 factorial times r. So this is the same thing as, well, r minus 1 factorial is 1 times 2 times 3 times all the way up to r minus 1. And if I multiply this by r, so this would be, of course, simply r factorial. So r minus 1 factorial times r is just simply r factorial. So that there I could write r factorial. And then the next thing that I have here is basically n minus r factorial. N minus r factorial times n minus r plus 1, which is the same thing as, by the same logic, it's n minus r plus 1 factorial. Or you can write it as which you can write n plus 1 minus r, n plus 1 minus r factorial, right? So now basically putting these together, over here I have n plus 1 factorial, and over here I have r factorial n plus 1 minus r factorial. Now if I had, now you know that the formula for n combination r is the same thing as n factorial over n minus r factorial times r factorial. Now if I had, based on this, if I had n plus 1 combination r, that would be equal to basically n plus 1 factorial over n plus 1 minus r factorial times r factorial, which is exactly this thing over here, n plus 1 factorial, n plus 1 minus r factorial times r factorial. So then you can say that basically this thing is equal to n plus 1 combination r, which means that basically n combination r plus n combination r minus 1, which means that n combination r plus n combination r minus 1 is the same thing as n plus 1 combination r. That's basically the theorem that we wanted to prove, and that's the theorem number 6. Now we have a couple of examples here. Let's go through these examples, and we are practically done with this chapter, except for we have a couple of also miscellaneous examples and that sort of thing, but the concept in this chapter has already been taken care of. So I'm going to end this video, in the next video we will work on the examples, and see you in the next video.